So I'd like to invite, I think, if Rika, John, Dana, and Famia, if you're around, to join us. Nice. Let me add you. Brilliant. Thank you. Please let me know if I've missed anybody. But I'd just like to maybe come back to all of you in response to Jonathan's talk, from your different perspectives, or how does this tie from your different perspectives? How does this kind of approach for physical hardware combined with this semantic intelligence fit with the kind of approaches you're thinking in? Any thoughts in response to the talk?
I'd love the opportunity to be controversial.
Please.
To push back a little bit. So for context, I'm a professor at a small liberal arts college, right? So it's our job to ask these questions. I would stipulate that I want to be argued against here, that LLMs are the opposite of embodiment. That they are sort of the quintessence of an anti-embodiment approach to AI. So I'm really curious how, Jonathan, I'm putting you on the spot, you lined up LLM with cognition in sort of the model of a robot, and I just wanted to push back a little bit, because I have to spend all of my days explaining to my administration why not to use LLMs for anything. And yet, but that said, this is awesome, right? The work you're doing is awesome, don't get me wrong. But is it cognition?
First of all, I really appreciate tough questions. It's really fun to argue about stuff. Second, you're right. I think I've been a little bit loose with words. Cognition is, I don't know what other word really to use. I think of LLMs as the ability to bring in human context to something in a way that in robotics has been incredibly difficult in the past. You can just look at an image and say, identify the things in the image. The LLM will just throw it back at you. Say, that's a microphone, that's a door, that's a picture on the wall, and it'll describe a scene. That's amazing and never been done before. So having that contextual information is very, very useful in then getting your system to make decisions about that information. Now, I would not say that LLMs are necessarily that good at making decisions, at having intent or having a plan for what the robot should do. And that's kind of that middle layer that I still think is a little fuzzy for us. I know how to do the physical intelligence and say design a behavior that can walk and run and grasp and pick things up and move them. And we know how to sort of set up a workflow. And for something very structured, like I was saying, to clean up this mess demo, let me ask you this. How would you think about, we want to use the words cognition or LLM, we said, Digit, clean up this mess, and then Digit did. Is there any cognition going on?
I'd say there's tons of cognition, but not much of it is happening. None of it is performed by the LLM. I think a lot of it has to do with all the work that went into training the LLM, right? But the LLM, it can't learn, right? It can't adapt. It's not a dynamical system. It's a spreadsheet, and it's a spreadsheet that's a solution, to some linear regression problem. And it doesn't know what a mess is, right? There's no knowing there, and there's no reasoning there. It's exploiting the labor of millions of unpaid people who tagged photos with bubble wrap and cardboard boxes and stuff like that. But it hasn't solved any of the big problems of cognitive AI, like the framing problem or anything resembling planning. It's just sort of telling a story.
So maybe it's like there's a saying that there are no good models, but there are useful models.
Yeah.
So all of you say is true, and yet we asked it to clean up this mess, and it did.
Yeah, and you can't argue with things, right? That's awesome. But the only counterpoint, and then I'll stop talking. is Rodney Brooks, back before he sold out, said the real world is its own best model, right? And I mean, you've done amazing stuff with sim to real, but sort of it, the embodied intelligence community, needs to pay homage to its roots of purely embodied sort of physical intelligence. But anyway, I've talked too much. This is really amazing work. So really fun to see. I will yield the floor to my colleague Fumia.
Thank you, John. Can I just step in? Just following up this discussion of LLM, I think Jonathan, you made a really good, interesting statement about LLMs are good, are not really good at planning, and I think exactly the same Rodney Brooks said the same thing. Like LLMs are good at reacting, but not really good at planning. And I think there's not really much complete clean cut difference between reaction and the planning. There's something in between, but I'm just wondering what's your experience, Jonathan, about is this actually the case that the LLMs are good at reacting? If it's a short-term planning, is maybe it's able to handle, but as soon as it goes to longer term, it's becoming more and more hallucination. What's your experience, and do you have any comments about it?
Yeah, like my biggest comment is I don't really know what planning is. And so you saw in the video, for example, I showed Cassie going up the stairs, and where it caught the toe just right on the edge of the stair, then fell backwards, placed its foot, recovered, and then went back forward. That looks like planning. Maybe it is, but that was a reinforcement learning approach. There was no explicit planner. It was just that we had, there's some memory because it's a PPO approach. So it does know something about its history. But it's kind of a black box in there. And then we just threw, decades of hours of time of the robot trying random stuff until it kind of came up with a policy that you just takes in all of the encoder values and the inertial measurement and outputs, torque commands to the motors. And I don't know. Do you think that was planning? I don't know. When
No,
digits going around and
that,
picking up the different objects in that space, is that planning?
I think
we didn't
that really
explicitly
illustrates, we really don't know much about cognition, and we cannot really define what planning is. So I think this is where we are, and I think it's a really interesting discussion. I just want to ask you another, really provocative question, so to speak. So, leg versus arms, right? So you mentioned that the legs and the locomotion and the manipulation are kind of similar thing. I kind of agree with it to some extent, but the more and more we do manipulation problems, they are actually very different. And we had a really discussion yesterday about the hard embodiment and the soft embodiment in terms, in the context of how much complicated, complex interactions, system and environment interactions you have. And then, legs are, of course, very complex, but compared to what we do with human hands, I think interaction is rather simple. So I just want to have a bit of discussion. What's your views on how far you can go with the manipulation and the robotic hands, and whether this is a physics-based approach or simulation-based approach? How far can we go with this kind of technologies? Can we go as far as with the legs locomotion, or we're going to soon see the limitations of what we can do with the manipulation in the near future?
Sure. There certainly are differences. Like one of the biggest differences is that legged locomotion can be very cyclic. So you can settle into a behavior that is a repeating thing, and you can stabilize it because you've kind of got this something like this sine wave, and if you diverge a little, it just needs to kind of come back to the cycle. Whereas a lot of manipulation is kind of single shot, But I feel like it's some sort of a continuum as well, because I think of it as loco manipulation. And an analogy to this is, what's the difference between walking and running, right? There's obviously differences between them. And for a long time, they were really viewed as different things. And you could think of a inverted pendulum walking robot, the passive dynamic walkers that can slowly walk down the hill, were all rigid body things. And we think of running as spring mass, but then I think it was Hartmut Geyer and Andre Seyfarth that showed, hey, the spring mass model can show all walking and running gaits. And a quadrupedal form, David, he was drawing a blank on his name right now, maybe you can remember, showed that like a quadrupedal version, only passive springs and masses can reproduce every single natural locomotion gait, you know, quadrupedal, bipedal, etc. That's amazing, right? So it kind of took people from thinking about two different models to this is kind of unified, and there's just, in one sense, the energy of a particular, you know, dimension in that model goes to zero, and then in the other direction, in a different part of that goes to zero. It's just a broader model. How about people who are climbing a rock wall? They're using their legs for manipulation. You know, think about, like Matt Mason would often say, that walking and running is just juggling yourself. So, okay, that's enough of the high level stuff. I would say that for another example of manipulation that I really like, you think about like form closure in order to grasp something. And I know that long ago, Chris Atkinson made a juggling robot with an old Sarcos humanoid. And the thing that really stood out to me as an important concept that should, I think, apply to almost all manipulation tasks is the idea of finding positions and locations in your locomotion that are stabilizing, that bring your uncertainty to zero. So when he was juggling, you throw the ball in the air and the ball is going to have some uncertainty and follow some range of trajectories. You don't really know what they are. And to catch it on the other end, he made hands that they were just a cone, you know, so that the ball would land somewhere in the cone, but every time it would come back to a known location. So I think, and Matt Mason did this too with, like, you know, how do you sort things? You'd have a tray with objects in it, and if you just tip it this way, this way, now you know what orientation it's in without any necessarily sensing. I think an awful lot of what we do with our manipulation is conceptually like that. It's not super high precision perception of everything and then super high precision position control. It's using your environmental constraints, or putting a key in a door. How a robot might do that is super high precision within a few thousandths of an inch versus a person who's like drunk, you know, slap the door with the key, slide until they catch the keyhole, and then the key goes into the. So that's using the constraints in the environment, a compliant interaction with the world, and gathering information with that interaction that isn't just about perception and precision. So certainly differences. I think that manipulation is going to be something where, you know, everybody is trying to work on it, and it's certainly solvable because we can all do it. So I don't know, we're going to see a lot of progress here.
What about the hardware side? Because as you said, that was something that was a breakthrough in terms of locomotion. There's very different challenges for manipulation in terms of the number of actuators, the distributed sensing.
You're right. So that's okay. So talking about hands, when you see these 5-fingered hands and they can move around, I see this as an animatronic, you know, kinematic piece of art, but I don't see it as capturing any of the inherent physics that actually matter for dexterous manipulation. So you can do things that are inherently kinematic, and there's a lot of, just like humanoids can place one foot in front of the other and walk around on flat ground, but it's not very robust. Kinematic 5-fingered hands can do some basic motions, but it's going to be very brittle, not very robust. To do real dexterous manipulation, it's going to be analogous. You're going to need the same kind of compliant interaction with the world and the real sensitivity to the forces that you're applying, and the ability to have it be insensitive to disturbances. So when you pick up something that's bigger or smaller or heavier or lighter, it doesn't really matter because you're just kind of mashing your hand around it. And you're absolutely right. At that scale, making a lot of small actuators, biology is good at that with many small muscles and tendons, and robotics is not. It's much easier to make a big motor and a big gear train. So that might make it more challenging, you know, than locomotion. And that's also why I think that the best dexterous manipulators are likely to be 2 fingers or maybe 3, you know, as simple as possible in order to get really exceptional behaviors.
Interesting.
I'd like to ask, oh, you go? Okay,
No,
yeah,
please,
I wanted to
Rika.
ask about adaptation. So I'm a big fan of your work all the way from Atreus. I actually ran a few experiments on Atris, so a fan of, assume the robot is a sphere and simplifying hardware. And that's what I guess allowed you to really kind of close this inter-real gap, because you addressed it from the hardware side, right? But especially in manipulation, we have cases where we can't close this inter-real gap, we don't have information like friction, right? And so we have to sort of adaptively close it online, in real time in the real world. What are your thoughts on the adaptation methods? So, yes, suppose you've trained in sim. Yes, suppose you made a best effort to make high quality hardware that is, has some notion of what the forces are in the environment. What do you think about the adaptation methods, or, how to maybe make the hardware somehow adaptive as well?
That was a tough question. I do think that sometimes you're trapped behind the hardware and there's nothing you can do about it. It's like when we went from, on Atreus, we had a fiber optic gyro that gave us the inertial measurement, the orientation. And it was 5 pounds and took a lot of energy and was $18,000. And it was fine for a research machine. And, to give you an idea of its precision, when we bought it and the students were just had it on the workbench and were testing it, they were like, man, it's drifting. This shouldn't drift. The specs say it should be much more stable. I don't know why it's drifting. They finally figured out it was drifting 360 degrees per day. So it was measuring the rotation of the Earth, and that's the drift they were measuring. So when we put it on the robot then, we had to point it north to calibrate it. And then if we were running for a few hours, we had to recalibrate it. But it was that good. And that precision, that ability, meant that we didn't have to worry about filters, estimates, it just straight in. On Cassie, we used a MEMS gyro, which was way noisier. And there are so many challenges with having the estimate of the orientation of the robot. And it was almost good enough. But if it wasn't quite good enough, if you're using, sensors that aren't quite good enough, there's nothing you can do. You're just trapped behind the limitations of the hardware that you've got. And I think with manipulators in particular and friction, you lose all of the information. It's gone. So think of it this way. Think of a 1 degree of freedom, actuator that's pushing against a wall, something that's movable, right? And you want to apply some force, call it 10 newtons, but you've got 50% friction in your transmission to do that. You don't know if that wall is pushing against you or you're pushing against it, whether you're back driving it or forward driving it. And so you don't know if you're applying 5 newtons on the wall or 15 newtons on the wall, and there is no way to know. Now, maybe you can try and build models that do that. And once you've started moving a little ways, you know which direction you're going, and then you try to compensate for the friction with the friction model. But every transition is going to be a weird, discrete, noisy. There's nothing you can do about it. The information simply doesn't exist. So, that's why I say that the AI is trapped behind the hardware.
Yeah,
you have to be able to make the hardware that at least in the ways that matter will be good enough. And then there are a lot of ways that don't matter. And the trick is knowing what that is. And same for the sim to real. When you're doing your training, you can't make the system robust to everything. You can't say the robot might have anywhere between 0 and 1 million limbs. It might weigh between 0 and 1 million kilograms. Might have between 0 and 100 friction. You have to actually choose what's the stochastic range of the things that it will see, and then only sometimes is there a solution. So that's one reason why trying to reproduce animal behaviors is possible, is because we have a proof of possibility there. We know that it's possible. And so that, sometimes there may not be a solution for something. I don't know.
I see. Yeah, it's interesting. I was recently at a workshop, which was actually primarily a manipulation workshop. And when there was a poll around the room, what do we need, computation or improved hardware? Unanimously, people said computation. And I said, what? We need better hardware. And it is really, really strange to hear something like this. But I think it's because it's what maybe John was referring to earlier. It's we have these LLMs, we are now empowered and we can solve kind of everyday tasks that we weren't able to solve before, but they're still very simple in terms of their physics. And so we might get stuck behind this. Yeah, you're limited by your hardware. So yeah, it's good to hear that. This opinion.
Yeah.
I was just wondering to change the topic a little bit back to the kind of the human-centric aspect. And Jonathan, you said that our robots should match the environment we're working in for humans. But as kind of robot capabilities evolve and perhaps human ones, is there perhaps at some point going to be a switch where we actually start to design environments for robots and humans, or for robots, maybe agriculture could be one, for example. Do you think this could happen going forwards, or do you think it's really going to be our robots must fit in with a human environment?
I guess I would say that our approach at Agility Robotics and our strategy is to make human-centric robots. But certainly mobile robots, farming robots, manufacturing robots, lights out warehouse distribution systems like, Ocado, or they have these big grids, that are moving all the boxes around the Borg cube of logistics. Those things are all going to be really important for our future as well. That's going to thrive. There's going to be probably more specialized robots than there will be multi-purpose robots. All of the above, there will be a lot of robots in the future.
And just to bring back on one topic we discussed quite a bit earlier was kind of emotion and expressing non-verbal communication between humans and robots. And that is a big also part of kind of human-centric robot interactions. I wonder if that's anything that's on your horizon, or anyone has any thoughts about how important is that? If it complete the task, perhaps it doesn't matter. Or how important is that kind of non-verbal kind of communication?
Well, it depends on the task. If the task is not next to people and it's just picking up totes and moving them around, then it isn't important. But if the task is working alongside people, then you need, for example, just pick the safety case. The robot has to be able to respect people's personal space. So in other words, interpret where the people are, interpret cues of when a person's about to turn right or left or what they're going to do. And the robot has to share those same cues with the people around it so that the people are able to respect the robot's personal space. So even just the simple task of walking down a hallway and you're going to turn left, how do you indicate which way you're going to go? There's a lot that people do that are very subtle cues of leaning in a direction, something like that. And the robots will just need to be able to communicate on our terms like that. So it is functional. And if you look at, that's why I talked about it being human-centric rather than humanoid. Digit's face is not like our face. It has two very simple eyes. And those eyes can animate very simple things so that it can tell you which way it's about to turn, or, what it is focused on. And that's it. Like, we designed it to show nothing but that. And there are no ears because you can't talk to the robot yet. And there's no mouth because it doesn't talk yet, because that's not very functional and won't be useful yet. So that's part of setting expectations with the design.
I just want to ask you, in the same line of discussions, the one a really impressive part of Jonathan's work is engagement of industry, which you think is very important at the end. Many of us have very little experience how to commercialize or how to make our research useful in the end. And I'm sure, like locomotion is such a fundamental basic function of any robot. So I'm sure you could think about hundreds of different ways this can be useful, but then you pick up, I suppose it's one type of applications in logistics, or maybe a few, only a few out of hundreds, right? So maybe you could just tell us a little bit about, your struggle or your mistakes, or how you made it actually successful to make it, commercially viable in the end.
That's such a good question. If there's one thing to say about it, it's having the right team. It's having the right skill set and the right talent, the right people around you. I've learned a lot, doing this commercialization, because it's a totally new experience. I remember, for example, starting as a professor and writing my first NSF grant, really around what the instructions were. There's a lot of guidelines on how to really write a grant well and what they expect. And boy, I worked hard on that, and I'm very proud of it. And it was completely dead on arrival. Like, it was clear that it wasn't even in the running or even close. And it took a while of understanding the culture around NSF and serving on a panel and understanding how people are actually feeling about all these things, to then be able to write it and be part of it. Well, none of that translated to startups and investors. It is a completely different world, and it was just like landing as a complete rookie again. And then the other piece of it is, kind of learning what is it that I'm good at and excited about. And I can tell you, I'm excited about the puzzle. I'm excited about trying to understand, how does manipulation work? What are the tools I can use to make that work? And when we get to, or locomotion, physical interaction in general. And when I can get to the solution and say, here it is, this is the answer, this is how this will work. We're 5% there, you know? And there's a stunning amount of effort and work in making a machine that is a product that meets customer requirements. There's an entire product organization that's engaging with the companies and writing down this incredibly lengthy document of what are the specific requirements of the robot that the engineers are going to design, and then building a whole organization around creating that machine that is going to serve the purpose of the customers. And, you know, I'm not actually that good at that. Also, all of the aspects of what's your business model? How are you going to make money? How are you going to build out the financial side of all of this, get investors excited about it, and have a reason why they feel confident that they are going to make money with your business, which is going to be selling and providing value to customer? That's also something that is a talent, and some people are very good at it. So building the team. You know, I was never the CEO of Agility Robotics, and that was a great choice. I teamed up with my great friend from graduate school, Damien Shelton, who, you know, when we were grad students together, he's the one that negotiated the healthcare contract for the graduate students, right? Just volunteered to do that. So it's like that was his inclination and his talent, but he was also new robotics. So it was a great partnership to start with. And I started the company with my you know, one of my very best graduate students, Mikhail, who in the whole lab of PhD students and postdocs and everybody, he was like the pragmatic one that absorbed everything and is like, well, why don't we just do this, and programmed it and made the robot work, you know? So he was the chief engineer, and that's a real talent. And it's a talent that, you know, he was on the software side of things that I don't have. I'm not a software engineer at all. So that was the starting point. And then from there, you've seen that I've stepped back from CTO. We hired Melanie Wise. Melanie Wise, you know, founded Fetch and sold it recently to Zebra, and was very successful deploying 1,000 robots and more. And so she is steeped in how do you create a product? How do you ensure that you're meeting your customer requirements? How do you deploy robots and service them? A whole skill set that I don't have. So I, you know, stepped into the chief robot officer role, which is much more about looking forward. How are we going to, in 2 years, in 1 year, what are the technologies going to look like? And what's the vision for a robot as we move forward? That's more a match to my talent and my interests, but it's just critical to be able to find the people who are good at all the aspects of the business that you aren't. It's tough on your ego. It's steep on the learning curve. It's incredibly challenging, but that's probably the most important part of commercializing something.
Thank you very much. That's inspiring and lots of food for thought. Thank you so much, Jonathan. And thank you so much for your time. Thank you to all the panelists. So I think that's us for today. So thank you once again. And just to briefly summarize where we are, we're now going into the final session of breakout rooms for today. So do stay around. In about 30 seconds or a minute or so, these will open up, and so there is another series of talks. And then tomorrow morning we are back again starting at 9:15 UK time with the final plenary talk from Charles Spence and another set of talks and panel discussions. So just once again to say thank you today to all the speakers throughout the day, and thank you all for participating. A reminder that the talks are online, and then we will move to the breakout rooms and see you all tomorrow. So these should now be the 3 breakout rooms we should have: human-centered systems, computational approaches, and cyber-physical systems. So please, if you're having any problems joining these, just put the number of a room when you want to move into the chat, and then we'll move you. But thank you very much, everyone, and thank you.